Okay, let's jump right into this explainer. We're stepping into the high-stakes world of analytical chemists. When we hear the word detective, we usually picture trench coats and magnifying glasses, right? But the scientists in these labs, they're our modern environmental detectives. They're literally out there hunting down invisible, dangerous toxins in our water and our food. It's a wildly fascinating process. And today, we're going to break down exactly how they use these incredibly powerful instruments to crack the case. We have a great roadmap for today. We'll start by detecting the invisible, look at exactly how fluorescence detectors work, and figure out how to make the invisible glow. Then we'll dive into real-world environmental applications, check out refractive index detectors, and finally, wrap up with the ultimate identification tools. So, Part 1, detecting the invisible and the search for trace toxins. First, we really need to set up the overarching problem here. Think about the water flowing from your tap. How do we actually protect that water, or the food on our plates for that matter, from trace amounts of pesticides and industrial pollutants that we can't see, smell, or taste? The big question is how we detect these invisible culprits as they elute or flow out from a liquid chromatography column. They're completely mixed in with the mobile liquid phase, so we need a highly specialized set of eyes to spot them. And that answer very often lies in spectrofluorimetric detection, which relies entirely on fluorescence. Simply put, this is the ability of certain compounds to re-emit part of the light they absorb from an excitation source. Think of it like a highly selective glowing fingerprint. Now, only about 5 to 8% of all existing molecules possess this natural fluorescence. But for the ones that do, well, when you hit them with a specific light, they absorb that energy and literally glow back at you at a completely different wavelength. Moving on to Section 2, how fluorescence detectors work, and capturing that glowing fingerprint. Let's slow down a second and talk about the actual mechanics of a fluorimetric detector. The geometry inside this instrument is absolutely crucial. To avoid being completely blinded by the intense incident light beam that excites the sample, these detectors measure the emitted glow perpendicularly. It's a strict 90-degree angle to the excitation source. The sample flows right through a central flow cell, gets zapped by the excitation radiation, and its fluorescent glow shoots out sideways to be measured. So the big takeaway here is that the intensity of this fluorescence, the sheer brightness of that glow, is directly proportional to the concentration of our target chemical. But there is a catch. This mathematical relationship only holds up as long as the concentration is kept really low. If the solution gets too concentrated, the molecules actually start reabsorbing each other's light, and that totally messes up the data. But in dilute solutions, a brighter glow simply means more of the toxin is present. Section 3. Making the invisible glow through the art of derivatization. Now this leads us to a massive challenge. What happens when we're tracking a dangerous chemical that doesn't naturally glow under our analytical flashlight? Remember, only a tiny fraction of molecules naturally fluoresce. So how on earth do we handle non-fluorescent hazards? Things like trace carbamate pesticides that might be lurking out there in agricultural runoff. Chemists use this incredibly clever, almost magical workaround called derivatization. This can happen either before or after the sample goes through the column, so pre- or post-column derivatization. Basically, if the molecule won't glow on its own, they forcefully attach a glowing tag to it using a precise automated series of chemical reactions. For trace carbamates, it's a specific step-by-step dance. First, they react the compound with sodium hydroxide, and then they add a reagent called ophalaldehyde, or OPA. That specific reaction transforms the methylamine group on the pesticide into a highly fluorescent derivative. And the tech that does this is brilliant. A flow cell device is inserted right between the chromatography column and the detector to completely automate this reaction. As the invisible chemical exits the column, it passes through this microcell where that OPA reagent is automatically mixed in. So, right before the detector's eyes, this invisible pesticide is transformed into something that brightly fluoresces. Suddenly, it's perfectly measurable. Section 4. Real-world environmental applications, specifically spotting pHs. Let's bring this back to why this matters for you in your daily life. When the final data rolls in, it generates a chromatogram full of distinct, spiky peaks. That is literally what environmental safety looks like in data form. It shows the precise detection of dangerous polycyclic aromatic hydrocarbons, or PAHs. These are toxic compounds often found in drinking water as a result of industrial pollution. By using specific excitation and emission wavelengths, the fluorescence detector can pick out each individual PAH, like pyrene and chrysene, as its own distinct peak. This is exactly how we ensure our water meets strict legal safety thresholds. Section 5. Refractive index detectors, the universal backup. So let's keep building our detective kit. We know fluorescence is highly selective, but what's our universal method? What if we need to see everything? That brings us to the refractive index, or RI detector. When you compare the two, they're practically opposites. While the fluorometric detector is incredibly sensitive and super selective, the refractive index detector is an almost universal backup. It can spot almost any compound. The trade-off, though, is that it's really not highly sensitive. And as we're going to see, it is notoriously dependent on perfect temperature control. The RI detector works on the Fresnel principle. Think about what happens when you look at a straw resting in a glass of water. The light bends, right? It makes the straw look broken. That's refraction. This detector measures exactly how much an eluting compound bends a beam of light inside a very special cell. Let's break down the mechanics inside the instrument. The light travels through a cell that's divided into two compartments. One side is continuously filled with the pure liquid mobile phase to act as a baseline reference. The other side receives the actual flow coming right off the column. When a chemical analyte passes through that second compartment, it changes the refractive index. This bends the light, causing an angular displacement of the beam. Inside a dual-stage photodiode, the instrument actively measures the exact amount of compensation needed to recenter that beam. And that exact measurement, that becomes our data peak. Now, there are some very strict operational rules here. Because it's measuring universal light refraction against a pure reference, the baseline can swing into either positive or negative signals, depending on the chemical. But more importantly, the refractive index is wildly sensitive to heat. This equipment requires incredibly strict temperature control. We're talking down to 0.1 degrees Celsius. Otherwise, the baseline drifts all over the place and gives you completely false readings. Finally, Section 6. Ultimate identification tools, moving beyond retention time. To wrap things up, we have to acknowledge a fundamental truth of chemical detection. Simply knowing when a chemical exits the column, its retention time, is really vulnerable to error. I mean, two totally different chemicals might just happen to flow out at the exact same minute. It's not always enough to make a positive ID. So scientists inject standard, known compounds to verify these times. But to run a true, undeniable background check on a suspected toxin, they couple these liquid chromatography columns with some incredibly powerful tools installed right at the end of the line. We're talking about mass spectrometers that literally smash the molecule apart to read its fragmentation spectrum, and high-field nuclear magnetic resonance, or NMR instruments. And thanks to miniaturized probes, modern NMR can now identify the exact atomic structure of a substance from mere microgram quantities. It's unbelievable. It really is a marvel of modern science. Knowing that we have the technology to trace microscopic threats in our environment, whether we're making them glow, measuring how they bend light, or mapping out their entire atomic structure, we just have to ask. With the power to detect mere micrograms of a substance, what invisible mysteries will these analytical detectives uncover next? It's definitely a comforting thought knowing these incredible instruments are constantly standing guard over our environment. Thanks for joining me on this explainer, and keep your curiosity bright.